So you are welcome to PHY406 class. That's Optics 3. I hope you can all hear me. Last week, we did a little bit of introduction of the course. And we discovered that the course material is about 79 pages or thereabouts. So the implication is that we are to, in as much as it looks small on the surface, can you, I hope you can hear me?
Yes, sir, I can hear you.
Yes, sir, okay, sir.
Good. So it looks small on the surface, but it is voluminous. So you need to do extra work to cover the course content. And as you are all aware, this is not the normal conventional class in your previous secondary school where you can actually, how am I going to put it now? You will be taught. This is a facilitation class in which you will be asked to read up, come to the class, and at the end of the day, you ask questions so that I throw more light to the gray areas you might have in the course. So as the case may be now, we are starting with Unit 1. Unit 1. I hope you've all downloaded the course material.
Yes, sir.
And we have a very short time. We have just 40 minutes to go through the course material. So I have a slide I'm going to share with you now. Probably still loading. So as I always say, this class holds every Monday. So on the chat menu, please, can you, if you are not on the WhatsApp group, that is, I'm talking to Lucky, Egede, and Abdulaziz, please kindly type your phone number there so that someone can pick it up and add you to the WhatsApp group,
okay,
where we can actually interact more. So I've designed the course, I've designed the course content in such a way that we will be able to cover it within few weeks. Now, let's look at the material for the course. It is 79 pages. Let me share it on the screen. So this is the course material. This is the course material. It is about 79 pages, but it is loaded. Having gone through the material, it's correct, it is quite loaded. So I divided this into 4 places in which I said Unit 1 will be taught for 2 weeks. But due to the fact that we didn't hold any class last week, we had an introductory class last week in which we were able to just introduce ourselves, fix the time, and knowing fully well that we have a short period due to the, I don't know what's wrong with the Zoom app. Normally we're supposed to have unlimited time, but I guess when it is fixed, we can have our normal 1 hour for the class. So basically, I'm trying to see, I think I've covered the whole of this for what I'm going to share with you today. Okay, good. So I guess what we will do is that, okay, good. So you can see that the unit 1 stops at 22. So me, I'm going to, and the topic there is coherence. Can you see it here? Unit 1,
Yes, sir.
coherence. So I will stop share now. So we'll go through a little bit of coherence, and it is advised that you visit the online platform in which videos of these things are there. The instructional video are there. You'll be able to go through the course material in no time, get yourself acquainted with the course. So what we'll be doing is that you read ahead of the class, you come around, we share, you bring out the gray areas, then we look at the questions. There are some questions in the course material, we solve it together, and before you know it, will be good for your TMA. I guess your TMA will be coming up in a few days' time. So it is better that we cover at least unit 1 and unit 2. At least your test should not go more than that. So briefly, let me stop sharing this and bring up the slide. Okay, I have it here. Still loading. So PHY406. So the topic we are learning today is coherence. And I said, please, if you are having a noisy background, it is better for me to know because I can hear feedback from that, from underneath. So I guess you can see the screen now. Can you see the screen?
Yes, sir. We can.
Okay, good.
Yes, sir. We can.
Okay, let me just start. So what do you understand by coherence? So intended learning outcome. At the end of this lesson, students should be able to describe and explain the concept of coherence. Distinguish between the two types of coherence we have. That is the temporal and spatial coherence. Temporal and spatial coherence. And we should be able to relate temporal coherence with the width of spectral lines, and relate spatial coherence with the visibility of fringe pattern, and solve numerical problem based on coherence. Now, what is coherence? I said coherence is a property of light wave, and this occurs when two or more waves of the same frequency are in the same phase or have constant phase difference. So they are called, they can also be called coherent wave. I think you get that. And you can see as a diagram here, when we have two or more waves of the same frequency and the same phase, can you see they have the same shape, they're in the same phase, and they have the same frequency, phase and phase difference. Those are the two keywords there. Same frequency and same phase, or have constant phase difference, are called coherent waves. And I said here that hence we may say that the necessity of having coherent sources for observing interference phases essentially implies that the waves from two sources must have a constant and predictable phase relationship. Now, when we're talking about constructive interference, when we're talking about light being formed, it is as a result of waves that are of the same phase, that they have the same phase difference, and it is what we call constructive wave, assuming, or you can say constructive interference. Now, if they are of different phase, you will discover that they will negate each other, and we won't be able to have a constructive interference. But here we are interested in the constructive phase of the interference. Now, looking at this, you can see they are in the same phase, they have the same frequency, they are moving at the same frequency. Now, in general, sources and waves that emit this are said to be coherent if they have equal frequency and maintain a phase difference that is constant in time. So if you are trying to define coherence, you must use these two keywords, the frequency and a phase difference that is constant with time. So frequency and time are of essence here. Now, I said in the next point that if either of these properties is lacking, the sources are incoherent and the waves do not produce any observable interference. That means there is what we call destructive interference. They did not give us what we call, did not produce any observable interference. And I also said that coherence is a necessary condition for obtaining interference fringe pattern. Now, if as a prerequisite for this course, you must have studied optics 1 and 2. So when we talk about the mention the term fringes or fringe pattern, it shouldn't be strange to you. When the phase relationship is not constant, the point where the superposition light waves arrive in phase at one instance may receive light waves which are completely out of phase to it another instant. What we're trying to say is that the frequency of any wave moving in a particular direction, but or two or more waves in this case must have the same. They must have the same phase difference and the same frequency. We're just trying to illustrate what we have said earlier here. These 2 points, they are just what we're trying to illustrate further. So this results in a uniform illumination of the screen and no interference fringe pattern can be observed. So if they are out of phase, no interference fringes will be observed on the screen. Now let's look at the next slide. This is what we are trying to say. Now, you can see an incident light coming through a pinhole. Now, this is a young slit experiment. You can see an incident light coming and it passed through this pinhole. As it passes through the...
Sorry, sir, it has not been uploaded. Sorry, sir, the next page is not uploaded.
You said what?
The next slide. The next slide is not on the screen. It's the first slide. The next slide is not on the screen.
Okay. Let me
see. Slide you're talking about, it's not on the screen.
Let me see what is wrong. I'm coming.
Okay, it's there now. I think.
Maybe it's your network. Okay, did you see this?
Okay.
Did you see this before?
Now, I'm seeing it now. No. It was not there before.
That means you were not.
But I can see it now.
No. Were you with us before? You just joined up?
No, I've been since the beginning.
Okay. But you understand what I tried to explain, that we're just trying to say that.
Yes, very well, perfectly. I understand perfectly.
Okay, now we are trying to now describe this. I guess you can see this one now. This illustration.
Yes, very well.
Good. Now,
yeah,
we can see a light incident on a surface and it's passing through a pinhole. Now, let's look at this. So let E1 and E2 be the electrical fields Okay. Between electrical field associated with the light waves emanating from slits S1 and S2. We have young double slit experiment here. Now, the places when light travels through this pinhole and passes through this slit, this double slit. Now, the places where we have what is called coherent waves or light are the one that forms bright fringes on the screen. But the places where we have a kind of destructive interference, you can see what we have here. They are overlapping each other, so they are forming dark fringes. But when you see this, when we have bright fringes, they are not interfering. So we said that let E1 and E2 be the electrical field associated with the light waves emanating from slits S1 and S2. These waves superpose each other, and the combined electricity field at any point on the screen is given as this. So the combined electricity field associated with these two slits, S1 and S2, is given as E1 and E2. And you may recall that in the interference pattern, we observe the intensity of light, not the electric field. So here, when we talk about interference pattern, we are interested in intensity of light, not the electricity or the electric field. So since there's a relationship between the electric field and the intensity of light. So since the average intensity of light is proportional to the time average value of the associated electric field, so we say I, the intensity of light, which we are interested in, we are trying to relate the electric field associated with these two slits with the intensity. That's why we have I is proportional to the square of the electric field E. This E here. Is that clear? Is that clear? All this
very well, sir.
In your course material. I'm just trying to throw more light to it. I have about just 12 slides to just share with you, and by the time you go back to your course material, you'll be able to actually get what we're trying to say. Then probably next week you will answer some questions. Those we have from question 1 and 2, we are trying to bring the two together. I'm saying that I equals to E1 squared. That means the square of E squared, which is equals to then we are trying to expand this mathematically. We're just trying to do some mathematics there. Look at this. The E here equals to, we said square of E squared. So it is square of this E1, E2 multiplied by E1, E2. So expanding that was what gave us this. So it will be E1 squared plus E2 squared plus 2E1, E2. Now, having said that I is proportional to E, so we now replace the values of I in the E1 squared and E2 squared. So what we have here is I will now be what? The intensity will now be what? I1, intensity of the electric field as regards the slit 1 plus the intensity of slit 2 plus 2E1, E2. These are just basic mathematics. We have not done anything spectacular here. What we just did was to say that this, we said I equals to is directly proportional to E squared. So we just said E squared, that is, we are saying E1 plus E2 multiplied by E1 plus E2. So when we open up the bracket, that's when you have this E1 squared plus E2 squared plus 2E1 E2. For good student of mathematics, you should not have any problem with this. But what we're actually interested in is the end equation. So the equation above shows that the resultant intensity on the screen is the sum of intensity of I1 and I2 due to the individual slits and the interference term 2E1, E2. We are just saying that the intensity that you can observe on the screen is as a result of intensity from E1 and E2 and the interference term. So we are trying to show that interference and what's called intensity plays a huge role in what we can see on the screen, the intensity and the interference pattern. So if we have what we call a destructive interference, we have a dark fringe, and if it is constructive, we have a bright fringe. So the interference term is crucial because it determines whether the resultant intensity is uniform. It's uniform illumination of or a fringe pattern on the screen. So the contribution of the interference terms to the resultant intensity depends primarily on the phase relationship between the light waves emanating from the two slits. So it depends on the phase relationship. That's the phase difference. I'm just trying to illustrate what we have said earlier, a constant phase difference. Now, let us first consider the case when the light waves are in phase at one instance and out of phase at another instance. In such a situation, the product E1, E2 will be positive. That means they are in phase. The product of E1 and E2 will be what? Positive. At one instance, okay? I'm coming. In such a situation, the product of E1 will be positive at one instance and negative at another instance. So we are looking at when it is in phase, which will be positive, and when they are out of phase, which will be what? Negative. As a result, the time average of E1 E2 will be 0. That means if they are in phase or out of phase, the time average of E1 will be 0. That means this the value of E1 and E2 will be what? 0. So going back to this place now, when we have this E1 and E2 here, can you see the arrow? Can you see the arrow I'm pointing? Hello?
Yes, sir, we are seeing it.
Now, this
Yes, sir.
We are saying that if it is 0, when it is in phase or out of phase, what we're just trying to say that we're just trying to look at a scenario whereby the electric field here is 0. That means this equation is now reduced to I equals to what? I1 plus I2. So we're having this kind of phase relationship that's varying with times are said to be incoherent, and the resultant intensity will be I equals to I1 plus I2. That means when they are out of phase, when the product of E1 and E2 are negative. That means they will cancel out each other, so that this equation will be this part of the equation will be what's it called? The interference term will be 0. That means if we have this kind of thing, the waves of this kind of phase relationship are said to be incoherent, and the resultant intensity is given as I equals to I1 plus I2. What I'm trying to talk about is this. When they are in phase, they will give you a bright light. When they are out of phase, they will give you dark fringes of or dark light, as the case may be. Now, going through what we intend to achieve, we said there are two types of coherence. Can you imagine? We have just 10 minutes more. This Zoom, this thing is too short. Now, let me quickly rush through it. Now, I said coherence, which is essentially a correlation phenomenon between two waves, can be with respect to time and space. Thus, for expediency, we distinguish between two types of coherence. So we have temporal coherence and spatial coherence. Temporal coherence, which can be also called longitudinal coherence or monochromicity, applies to waves traveling along the same path. Now, it refers to the constancy and predictability of phase relationship as a function of time. Now, temporal coherence deals with time. It deals with the time or a phase difference. Now, I will display something here. Now, spatial coherence refers to the phase relationship between waves traveling side by side at a certain distance from each other. As the name implies, spatial coherence. Spatial coherence means the relationship between waves traveling side by side at a distance, spatial, space. Is that clear? Refers to the phase relationship between waves traveling side by side at a constant, at a certain distance from one another. And it is said that the further apart of the two waves are, the less likely they are to be in phase and the less coherent the light will be. So if the spaces between them are actually far apart, they will be out of phase and they will not be coherent. Now let's look at this diagram for temporal coherence. Now look at this. In the course material, it shows clearly. Now let's look at a wave, a sinusoidal wave. A sinusoidal wave is a light going up or a wave going up and down. And if it's starting at the origin, it's a sine wave. If it's not starting from origin, is a cosine wave. I'm just throwing more light to that. Now, if you see this type of waves, it starts at a particular point from the origin, 0. If you look at your course material, you see what I'm talking. And it comes and it ends at this point here. That's a phase. Another phase starts and it ends at a particular point, and another phase starts and it ends at a particular point. So what we are talking about is that the time difference are constant. They are not overlapping each other. That's what we talk about temporal coherence. They change, they increase with time. They are time dependent. They are not out of tune. They are not overlapping each other. They wait for their time. So when one wave's form starts or ends, that's when another one will stop. If you go through your course material, I'm just trying to throw more light. When you see this diagram, it was lifted from the course material. Now, temporal coherence can be identified by qualitatively as the interval of time during which the phase of the wave motion changes in a predictable manner as it passes through a fixed point in space. It is predictable manner. It goes up and it goes down. Another one starts immediately, goes up and it goes down in a predictable manner as it passes through a fixed point in space. And in wave motion corresponding to light from ordinary sources. A predictable phase relationship can be observed only within the average length of the wave trains on a time scale. What this simply means is that when it's moving in form of a train, the wave train, it is in time scale. It changes with time. It moves with time. When one starts, it stops at a particular point, and another one starts, and it moves at a particular point. It does not overlap each other. It's not as if another one is passing underneath it, just like what we described earlier when we tried to describe coherence. But here, and mind you, the source of light here is from a single source, and it is what we call monochromatic source of light. When it's moving from a single source, one will be, it starts from a particular point, it stops, another one starts and it stops, and like that and like that, on a time scale. But the wave, it moves like as if it's a train. That's why we call wave train on a time scale. Now let's look at the spatial coherence. Because of our time, we have less than 5 minutes. Now, this single source of light passes through, this light passes through a slit and it forms on a screen. Now, in order to understand the effect of extended source or spatial coherence on the interference phase, we consider the Young double slit experiment with an extended source. Can you see? This is what I'm trying to say with an extended source. You can see the source is extended. It's not like the other one that is just a single source. You can see it is extended, the arrow going to S1 and S2. Schematically, these two slits S1 and S2 with an extended light source. Can you see? S prime and S of width W. Can you see from here with W? The light from some point S in the source illuminate the slit and interference fringes are produced on the screen. Can you see interference fringes are produced on the screen? If the sources are consistent of just this single point S, as in the idealized Young's experiment, as in this, a single fringe will be observed, but a real source, which is something like this, that we were using the double slits, is produced on the screen. It is more clearer, or how am I going to put it now? It gives a brighter fringe when it is of a double, it's coming from a double slit. You can see this. This goes from a single source, light enters through the slit and it forms on a screen. But if you look at this other one, light travels straight into one of the slits and diagonally through the other slit. Now let's look at what I've just illustrated there. A real source S and S prime is however of finite size, and the fringe produced by illumination from other points of the source are displaced relatively to those due to S. So light from the extended source therefore produce a spread in fringe with a consequent reduction in the visibility of the fringe pattern. Now, what we're trying to say here is that what we have here, we will be able to see what's it called? A bright fringe here, but it will be small. But with an extended source of light, we will have a very, very, very big fringe, but the visibility will be very, 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 very small. I have a summary of temporal, those are the things you should note when you are reading through the material, because I have less than 2 minutes, because the Zoom app will go off anytime from now. So temporal coherence, also known as longitudinal coherence, is related with the width of the spectral lines. So the spread in wavelength is given as, or the change in wavelength is given as wavelength squared over LC. So the corresponding spread in the frequency of the spectral line is given as this. Now, what we will do is that you will go through this material. I will send it through to the WhatsApp group. I hope John Dennis has picked the number. Or you can mail me your number, your phone number. We add it to the WhatsApp group. I will drop this material. So what you do is that you go through this material and you go through your course material from page 1 to 22. So by the time we meet in the next class, we still treat this. By that time, you will now understand, because it may be sounding strange to you, or you may not be getting what we're trying to teach now, but go through the course material. Because we are limited, I would have introduced some other material for them. And you note this, what is an Ariana? Can you see? There's some questions, there's some things I want you to note in the course material as you are going through it. By the time we now meet next week, we now